Alright, are we live? Let's see. Hello! Hello and welcome. Excuse me. So, today we're going to go over yet another Leetcode question, Leetcode problem. Non-overlapping intervals. I am a little bit hesitant to get into this one. We'll see how this goes, though. We'll see how this goes. So, yeah, non-overlapping intervals. Let's give it a shot. Let's give that a shot. So, given an array of intervals, where intervals of I is start of I, end of I, return the minimum number of intervals you need to remove to make the rest of the intervals non-overlapping. Okay. 1, 3 can be removed and the rest of the intervals are non-overlapping. So it doesn't matter if they're overlapping on an endpoint. They can share endpoints, then won't be overlapping. So I guess these are open intervals, I suppose. Need to remove 1, 2 to make the rest of the intervals not overlapping. 2 of them. Don't need to remove any of the intervals since they're already not overlapping. Interesting. Okay. And there are 20,000 intervals, and the values are between negative 20,000 and positive 20,000. Oh boy. Okay, well they're all integers, so you might be able to brute force this somewhat. Interesting. So. I'm gonna lay down for a minute. I don't know the answer. I gotta sit and think about it for a while. Yeah, definitely need to ponder it. There are some thoughts, some possibilities. So, okay. What we want to do, what we want to look at is, let's see, 1 to 10, 2 to 11, 3 to 12. Just thinking, how can we achieve this? We want to remove as few overlapping intervals as is possible. So let's see. Let's ponder this question. Let's think about this. So, one to 5, 4 to, I'm just thinking like, Hmm. Sorry, I've got like a bunch of other thoughts in my mind too that are kind of distracting, challenging things. Huh. Hmm. Sorry, just give me a moment. Sorry, a little distracted. Um, it's kind of a hard problem. Hmm. Oh man. Oh. There are so many things that are just exceedingly difficult. Should be fine. Hopefully. Hopefully. I think so. It's definitely a bit nerve-wracking, these things. Let's see how it goes, I guess. Sorry. I have a lot on my mind, I guess. Challenging things. Anyway, putting those things aside, or trying to. As far as intervals, so intervals that are overlapping. How do you even identify all, let's say just identifying all of the overlapping intervals. What would even be the minimum number of overlapping intervals to remove? How would you determine that? And also determining the overlapping intervals to begin with in the first place. Like, let's suppose we could efficiently determine for each interval all of the other overlapping intervals. Now, I think there are a few different things that can be done. Since the range of values that we have to work with is actually relatively small, it's only 40,000 integers, we can actually, for each integer, determine relatively efficiently, kind of set up which intervals include that number. I think that's kind of challenging too, because they're open intervals, so that doesn't really work too well, actually, because you have 1, 2, and 1, 3. Technically, neither of them include 1. One of them doesn't include 1 or 2. One of them basically doesn't include any integers, but they're still overlapping. So that's a bit awkward. So I'm not sure if that's a particularly effective way to do it, after all. Yeah. I mean, you could do a quadratic time round robin to find out all of the overlapping intervals. I mean, there's that. I think sorting the intervals on the x-coordinate is something that can be done. And excuse me. Then you can say all of the intervals after sorting there to the right that have that are equal to or to the right that have a x-coordinate that is less than or a first coordinate. We'll call it x and y, or a and b. We'll say a is the first coordinate, the leftmost side, and b is the rightmost side. So any interval that has a larger a value, or greater than or equal to a value, that's also has a smaller b. It's also less than the b value for the interval that you're interested in. All of those will be overlapping intervals. So I guess you could create like a tree or something. Yeah, I mean, you could do a logarithmic search, I guess, to find. You do a logarithmic search after sorting on each of the sort by the x coordinates, and then search also on the x coordinates, but search for the b value of that interval. So, for instance, if you had like 1, 2, that b value, you'd find out how many intervals have an x value that's less than that b value. Yeah, so you'd have some index that you would end up with. That's going to be the first index where, the first spot where I guess you could do the first spot where you're greater than or equal to the b value, and then you can just subtract 1 from that pointer, and that's the last node that's less than the last interval that has a starting point that's less than that b value. All of those be overlapping, so you could do that in logarithmic time after sorting, and so you do an n log n time, you could find out the range of a point. Yeah, you'd find out a pointer, like a pair of pointers, or just a pointer in the list, which gives you sort of a range of all of the overlapping intervals, including itself too, by the way. Yeah. I guess you'd have to. The range would be defined by the pointer where you started with, and then the other pointer that you found in logarithmic time by performing a binary search. Yes, that's n log n time. You could find out all of the overlapping intervals. Obviously, you would increment the starting interval to not include not include the interval itself. So, I mean, technically it overlaps itself, but you don't need that to. Probably don't need to know that or use that in your algorithm. Now the tricky thing here is it's not enough to even efficiently determine all of the overlapping intervals. And that's all well and good, but that's still not enough. You want to do better than that. You want the minimum number of overlapping intervals that you can remove in order to have only intervals that don't overlap. Okay, so that's interesting. Well, if you have 2 overlapping intervals, you got to remove one of them, certainly. If you have 3 overlapping intervals, now the question is, do they all overlap with each other, or do they just overlap one with another and another with another? If they all overlap each other, right, overlapping is an undirected edge, undirected graph. So actually, you could probably translate this into a graph problem as well, I think. Ultimately, what we're looking for is we want to remove nodes from the graph such that I think it's that all of the nodes don't have any edges, right? You don't want any of them overlapping with each other, right? So we could draw an edge. There's an edge from A to B if A overlaps B. But we can remove all of the connected nodes, I guess, and then it's not overlapping. But we want to remove as few nodes as possible such that the result is not overlapping. Yeah, there aren't any edges. That's interesting. It's a really interesting problem. How do you remove as few overlapping nodes? I don't even know how that's possible, where really if anything overlaps anything else, you have to remove one of them, right? Necessarily. So only one can remain. I guess an example would be if you had A, B, and C. A overlaps B and B overlaps C, but A and C don't overlap. So you would remove B, you wouldn't remove A and B, or A and C. You'd remove B. I think that's kind of what it's getting at. That's interesting. So something that kind of makes me think like, well, you'd want to remove. I think if you greedily remove all the nodes that have the maximum number of edges, then I think that's a solution to the problem. I actually think that's correct. I think you're guaranteed to remove the. I think you're guaranteed to have the most nodes left over at the end if you do it that way. Yeah, that would be an interesting proof, but I think the reason is because the edges are undirected, but removing either side of the edge will remove the edge. You want to remove as many edges as possible with as few nodes as possible, which necessarily means you need to remove the maximal node, the node that has the most edges each time. Which actually that could change too as you remove edges, as you remove nodes. Yeah, pretty interesting. I don't know how to prove that, but I think it's correct. I think it's true that you'd keep removing until you have a totally unconnected graph. You'd keep removing the node that has the most edges, one at a time, in a greedy way. And then, as I said before, you would actually so what's interesting about that is a couple things. So in our list, our sorted list, you can produce the list of edges for each node using in logarithmic time, sort of as described. But you can also you can build the graph that way. Part of the problem with that, though, I think the graph could be quadratic in size, potentially, so you actually don't want to build the whole graph, I think. That's one thing. The other thing is, like, you could imagine a graph where everything overlaps everything, in which case you're looking at, or almost everything overlaps almost everything, you're looking at almost a complete graph, which should have, I think, a quadratic number of edges in the end. And so if you were to try to save in a data structure all of that information, it would be inefficient, right? It would be quadratic. However, as described, like, we can actually save this data sort of efficiently in n log n time by just keeping pairs of pointers into the sorted array. But there are a few issues here. So one of the issues is we don't want, we would want to be able to efficiently remove one of these pairs, or one of these intervals. We would want to efficiently remove one of these intervals. That's one thing. And also, the graph, I think it is efficient to remove the nodes, but we also, from the graph, but we also would want to keep a running list
of the largest, the node that has the largest number of edges. The node that has the largest number of overlapping intervals. We'd also want to efficiently keep track of that as well, which I think could be challenging. And it changes slightly because when you remove one of the edges, I want to say something like we should keep the elements in a set or something like that. Because when you remove one of these elements, all of the other intervals that that intersects or that overlaps with, you'd want to update the number of overlapping elements there, and then put that back into your, I guess, your array or your heap or what have you, or into your sorted data structure, in order to determine what the next largest is going to be. So that's kind of interesting. Can you efficiently find the largest? Sort of one at a time. If you could do that in logarithmic time and then remove that, then I think you're in good shape. Not really sure though. Interesting. I've got to think about this now, huh? Excuse me. Yeah, it's really interesting. I think the proof, by the way, to that the greedy algorithm, the quote-unquote greedy algorithm, works or is correct, is I think the proof is, so like, we need the graph. We need to get rid of every edge in the graph by removing a node each time. So every edge needs to go. The only way to remove every edge with the fewest number of nodes removed is to remove the largest number of, remove all of the nodes with the largest number of edges every time. Right, at every inductive step, I guess, you can prove that would give you the best possible answer, I think, inductively. Right, so I guess you can kind of go backwards. You could say, all right, well, clearly when there's only clearly when there's only one edge left, you just remove one node trivially. When there are two edges left, if they're attached to two separate nodes, then you remove just one, right? Doesn't matter which ones you remove. If they're both attached to the same node, then the optimal would be to remove both. And then if you have the next edge, you have sort of inductively, you would say it could either be on another separate pair where it doesn't matter which ones you pick at all. They're all the same basically. Or it could be on a particular node, and you would lose one less node if that's the case by removing the largest first. I think that argument's true in all cases, right? Like you could keep adding edges, and every time you'd want to remove the largest. You'd want to remove the node that has the largest amount. Yeah, I don't really have like a solid inductive argument to explain that, but that's kind of the idea. Yeah, it's just sort of always better to remove as many you can only, in order to, at each step, removing the most edges equates to removing the node that has the largest number of incident edges, and that's always the best option. I think at all steps. Yeah. Anyway, but the question is, okay, how do we determine in, let's say, linear time? No, we do better than linear. Let's do logarithmic time. Can we determine at each step in logarithmic time which interval has the most overlap? I mean, we can, in n log n time, we can find that value as described previously, but the problem is that once we remove that, all of these other values have one less overlap, and it's possible that now something that didn't have, it's possible that the thing that would have been best to remove next lost an edge, so now it's better to remove something else. Something like that. I mean, I want to say something like, well, why not reinsert all of the edges into the data structure? I think that's one issue or problem, is that once you remove that edge, all of the other values are not the same, I guess, something like that. I think we can use a set instead of a sorted array, right? Because moving things around in a sorted array is kind of awkward, although moving things around in a set is also still awkward, especially because this set, if we make the key really anything, actually, it doesn't matter if it's A, B, or a pair of A and B, or something that can be hashed. No matter what we make the key, actually no, not hashed, no matter what we make the key, or not the key, we could have a comparator between these tuples that we could custom define if we have to. What I mean is that whatever we make, whatever we make the key of the set, the problem is that certain values will be duplicates of each other, but we actually want to consider those. So I guess we would need like a multi-set. I think if we remove a node from the set, the whole thing kind of readjusts itself properly in logarithmic time, so everything kind of maintains the same order. But the problem is that we don't know anymore which of these nodes has the longest, larger of overlapping, largest number of overlapping intervals. Oh, I think we're back. That was interesting. Disconnected and reconnected. Yeah, I'm wondering, I could try to use a set, but the problem, like removing from the set, everything will stay the same way. Excuse me. But the problem is that, like, it takes n log n time to figure out which node has the most overlap. It's not necessarily, like, that's not very efficient. We need something that's logarithmic or better So that way we can remove each node one at a time as we find the number of overlaps. I want to do the maximum amount every time as well. Maximum number of overlaps. The thing that's tricky here also is, like, again, if you have like a complete graph, you could have like, you could do one pre-processing step to kind of attach a pair and a number of overlaps to each node, and then each time you remove a node, you just update every pair that it overlaps with, and that's kind of hard too, I think. You update every pair that it overlaps with, and remove that, remove that status, but also update all of the these numbers, like how many things that it overlaps with. Something like that. I mean, I guess the graph analogy is better. You remove the node, remove all the edges, and update all the other nodes. That the nodes are now, update the neighbor set of all the other nodes that it's neighbors with. And similarly update their position in, I guess, in a multi-set, which would be logarithmic for each node. But the problem with that is there are a quadratic number of possible edges, and so this could be kind of an expensive operation to do it that way. Yeah, there are sort of a lot of edges. Okay, I've got to keep thinking about this, keep pondering this. Also, while I'm falling asleep, I'm so tired. Let me take the headset out and just kind of think about this for a bit.
So I think I keep like falling asleep. I'm trying to stay awake, and I think I keep drooling, which is incredibly flattering. Not flattering, but what the right word is. But yeah, so I think I keep falling asleep and drooling, and then I have to like get up and wipe my face with something. I think I'm just really tired. Can't think of a data structure that can support what I'm trying to do, so it's definitely like sorting the list once can put things into a spot where oh, maybe we need an interval tree. Oh, maybe that's what we need. I didn't think about that. That would do it, wouldn't it? Because that would allow you to keep track of all the nodes in the subtree, where I guess all the nodes in the subtree would be. No, it's not subtree. It's sort of like a graph, but that would allow you to update all of the right nodes in one shot. Just thinking here. Wondering if an interval tree helps us here. I don't know. Maybe. Maybe not. Possibly. Let me keep pondering this. I don't actually know if that helps. think I figured it out. This is an interesting question, though. This is challenging. So, actually, I think what you can do is you have a multiset as described, and you can, in logarithmic time, any particular node or interval, you can determine how many overlapping intervals there are by performing an upper bounds check, or a what do they call that? A logarithmic search for the I think we said based off if an interval is a pair, so based off its second value, right? Its right side, let's say. You can search in that set for all of the search in that set for the first interval that's greater than or equal to that bound, and then decrement the pointer one time, and you'll have the pointer, the first node that's the last node that's less than that value. And then if you take the difference between that pointer and the pointer you started with, that'll count how many nodes there are. I think you maybe have to subtract one again. That'll count how many nodes there are in that range, how many intervals overlap, including the interval itself. So you can efficiently in logarithmic time count. You can dump all these things into a set, and then in logarithmic time for any interval, you can figure out how many other intervals that overlap with that interval. I think what should be done is you're going to remove one element from the set at a time, and what you're going to do is you're going to check how many intervals overlap, and if there's more than one, then what you're going to want to do is check to see, so you're ultimately going to remove one element at a time, so it's going to be an n log n algorithm overall. N log n time to put these elements into the set, n log n time to remove all the elements, and there's an extra logarithmic check, two extra logarithmic checks each time you remove an element. So what you're going to do is you're going to figure out how many logarithmic time, figure out how many intervals overlap the interval that you're looking at, right? I guess it'll just be the front of the set. And then what you're going to do is pick one of the intervals. So there should be the next value, and figure out how many intervals overlap with that interval as well. And what you're going to find, and actually what's interesting about that is actually it's every let me just think here. That's actually that logarithmic check that we just described. That's only to figure out how many intervals to the right overlap the interval you're looking at. Doesn't necessarily tell you how many intervals to the left overlap, which maybe we should also consider that. Yeah, we actually don't. Let me just think. Yeah, the intervals on the left that overlap would be I'm actually not sure about this. I mean, it might not matter, because I want to say that if there's an interval on, so yeah, let's say you're going from left to right, You say there's all these there's at least one other interval that overlaps on the right side. Then we know we can find also the number of overlapping intervals for that interval, right? Let's take the first one on the right. So we'll find that one. And what we want to do is we want to know which of those has more overlap. And the one that has more overlap is the one we want to remove. Yeah, ultimately. And actually, if they have the same amount of overlap, then we're going to defer towards the second one, the one that's either further to the right or... See, that's not necessarily true, though. If they have the same amount of overlap, then it's kind of challenging. Because the thing is, one of those nodes has to be removed. We know that. The question is, at some point one of them has to be removed, but the question is which one. And it seems, I want to say we can efficiently do this by removing them, just the larger of the two, one at a time. I want to say something like it shouldn't matter if they both have the same number of overlap, but that might not be true, because they might overlap with different things, and then depending on how those things interact with each other, once we start removing other nodes, that it might actually be kind of complicated how they're related to each other. We know they overlap each other, so one of them has to go. The question is which one should go. Certainly the one that has more overlapping parts has got to be the one to go. But what if they have the same number? I think if they have the same number, then it doesn't matter. I think so. Because, like, I want to say that, let's consider a case where they have the same number where it does matter. Let's try to come up with a counterexample where it does matter. Or prove that in all cases it won't matter. Right? Those are our options here. So, like a triangle where every node has 2. It doesn't matter which one you remove, because you're going to have to remove 2 of it. 2 of any of those 3 is sufficient. But oh, by the way, I think we don't have to use a multiset. Any duplicate intervals, you just remove all of the extra ones, because they all overlap with each other, so they all have to go, except for one. Possibly except for one. So actually, this is actually a little bit easier than I thought. Or not easier, but we don't necessarily need to consider a multi-set. I guess that's a little bit easier. Maybe easier. All the duplicates you just toss immediately. If you have... Let's see... if you have... I want to say something like... there's... At one point, these two things overlap with each other, maybe, or they overlap. Yeah, they overlap with each other at one point, and then they overlap with a bunch of other things. And they overlap with the same number of things, both of them. I don't think it really matters, because you're removing the same number of edges from the graph, which is what you need to do anyway. You just need to remove as many edges from the graph as you possibly can at every step. I want to say that it's fine. I've taken kind of a leap of faith here, but I think if it's true that you're trying to remove as many edges as possible in a greedy way,
like what I'm trying to say is that maybe one of these edges, what it's overlapping, overlaps a lot of other things. And so when you remove all these other edges that overlap a lot of other things, then what's left is a node that has a much smaller number of overlaps. And so you actually would want to prefer to remove the other node rather than, yeah, actually I think that's true. Yeah, that makes sense. So let's imagine like 3 nodes that have a ton of overlap with other nodes, and then these 2 nodes that have these other 2 nodes. One of them is connected to those 3, and then there's one other node that's overlaps with. So they overlap at one point, these 2 nodes, but so node A overlaps with these 3 other nodes that overlap with a ton of other nodes. And then node A also overlaps with node B. So A has 4 incident edges, and then B is similar, except the nodes that are incident on B, they don't overlap with anything. They just overlap with B. You would want to remove B in that instance. You would not want to remove A, even though they have the same number of incident edges. Because if you remove A, then these other nodes that you're going to remove anyway, you may end up removing more than is necessary. Whereas, or rather, I think you'll end up being required to remove B optimally anyway, because B, when you look at that group of 4 nodes on the right side with B and these 3 other incident nodes, you'll have to remove B. So you'll end up removing A and B, because you're going to end up removing all the same nodes on the left side anyway. The question is, like, even though you removed A, and then that means you're also going to have to remove B, when you could have just removed B and left A, removing A might cause you to not have to remove another node. Well, you end up removing all the nodes that A is incident on, which doesn't need to be that way. Including A, right? You don't need to remove A in the end. You didn't need to remove A. Yeah, so I think the greedy approach is actually what you're supposed to do. So I think we can't. I don't think we can easily find a replacement or like a different algorithm. Man, this is hard. This is a hard question. It's challenging. I'm gonna put the headset down again and keep thinking. I don't have a good answer for this. Okay, so I have an idea. I think it goes something like this. You count for each node the number of incident edges. So the edges that are coming into that node or going out of that node. I guess the same thing. Just incident. Then the number of edges. That sum of all the incident edges is going to be twice the number of edges. The total number of edges. So what you're going to want to do is you want to remove every edge from the graph. Now the question is, do you remove every node that has an incident edge? Because, like I said, you want to remove every edge from the graph. And when you remove a node, you're going to remove all of the incident edges, which you're actually going to remove twice as many edges as that node. Yeah, see, that's the tricky thing. Each time you remove a node, you actually remove twice the incident edges on it. And you don't necessarily know where all those edges, which nodes those edges were attached to. I'm wondering if you can go the other way around. I'm wondering if you could remove the things that are overlapping with only one thing. That seems kind of bad too. That seems like the opposite of good. That seems the opposite of what we want. Oh, I have an idea. How about this? Why not perform a breadth first search, right, from the node that has the largest number of edges, and then do a level order traversal, right? So we're going to try to find all of the nodes we want to remove from the graph. So we'll do a level order traversal, right, a breadth first search, starting from the node with the largest, one of the nodes with the largest number of edges. And so if we remove that one, then all of its neighbors are going to be updated with a smaller number of edges now, right? And so now we can consider each of those nodes. I don't know if a breadth first search is really what we want, but we consider each of those nodes, and what are we going to do? Do we remove any of those? I mean, I guess in time proportional to quadratic time, we'll just say in quadratic time, we can, well, cubic, maybe it's cubic time. Let's do like a naive approach first. So a naive approach would be to just find, for every node, determine the number of edges that are incident on it. I mean, even just building this graph in the first place takes, I think, n squared log n time. It's not very efficient. Well, let's see, how many intervals do we have? Because maybe this is not such a big deal, right? Like well, no, I think, no, this is always kind of bad. Excuse me. Yeah, 20,000, no. No, doing 20,000 with n squared is like 40 million. Excuse me, that's a lot. Yeah, it's a lot. It's probably too much. Okay. Excuse me. So, well then. I don't know, man. I gotta keep thinking about it. I don't have the solution. I don't know it. Something I've realized about solving these problems, this is really just like competitive programming tips and tricks. This really isn't this really doesn't need to be this hard, and this really isn't that hard. This is just like take a class, not a class, but just look up competitive programming techniques, and then all these questions will become really easy, and then all these interviews are a lot easier. It's really frustrating. I have to say it's extremely frustrating to think that like all you had to do is just like look up the answers and memorize how to solve these problems, and it's just very easy after that. That's like it's like infuriating to think about how much easier this could have been. Um, yeah, it's just like just practically memorization. Let me think about it some more though. I don't like doing that. I don't like it. Feels like cheating, I guess. Kind of looking up answers online, sort of um, looking up the different algorithms, the techniques. But that's kind of what it comes down to, I think. Let me come back to this. Let me think about it some more. Let me keep pondering it. Actually, I do have the solution to this problem. I just don't realize it. I think this is actually much easier and than I realize. Yeah, and I guess the problem that I'm having is I just don't recognize. I think I'm just doing the cost analysis wrong. So basically, the problem seems to be like what you could do is take all of these nodes now and count the number of incident edges. So now we're going just back to strictly to the graph problem, where we're going to remove the node with to perform a greedy algorithm with the node with the largest number of incident edges. We're going to remove those nodes one at a time, and each time we're going to update the number of incident edges for all of the edges that it's touching, all of its neighbors. And for each of those neighbors, they're going to be pushed into a different position in the set. And we're going to use that approach to figure out which node to remove next. So I want to say that if you already had this built, where you had the neighbor set was already pre-computed, and you could update all the neighbors their keys in the set quickly, efficiently, which I think you can. I don't know if we could build this graph efficiently though. That's maybe a challenge. I've got to ponder that one. Maybe I don't really know. But let's say we could efficiently update all of the neighbors. Then there's a logarithmic call that you have to do for each edge that you've removed. But the thing is, the total number of edges, even though it's a quadratic number, that's why I'm thinking it could be a quadratic number of times that we have to sort of update these keys. I don't think that's true, because even though there's a lot of these edges, and these nodes would get updated, if you have a node that has a lot of edges, and you remove it, then you've just removed a ton of edges in one pass. I mean, maybe I'm wrong. Maybe the cost analysis is such. Like, I don't know. I think because what's going to happen is at some point you're going to have nodes that don't have any edges incident on them. And I don't know. It's hard. Like, what about what if you had a complete graph? Like every node has the maximum number of edges, right? Let's do it that way. So let's say you have 5 nodes, and every node is connected to every other node. Everything overlaps with everything. And so now, which by the way, if you had that situation, you could just remove all of them except one. But that's beside the point. So yeah, let's say we have everything connected to everything else. We said, okay, any of these nodes we can remove, and they all get updated and moved to different positions in logarithmic time. And then, so we do 4 operations for the first one we remove. The next one we remove, we do 3 operations. The next one will be 2. The next one will be 1. and now we're gonna have 0 incident edges. Well, I think just updating all of the nodes. Yeah, I do think that's still quadratic time. Okay, never mind. I guess this is harder than I thought. Or is this challenging? Yeah, this is still pretty challenging. Shoot. Even creating that graph, I think in the first place is going to be kind of challenging too. Excuse me. How do we? What do we do? How do we? Excuse me. How do we? Um. Also, this might be a case where we would want to use a tuple, a pair rather, as a hash key for an unordered map, which I would need to could write my own custom hash function. Can use the I think that shouldn't be too hard. That'll be interesting to do. Be a nice exercise to do that again. Learn how to do that again. But I want huh. Excuse me. What do we do? Huh. What do we do? I don't know, man. I'm tempted to just go like do some competitive programming, learning, reading about like competitive programming problems and tricks and tips and tricks, and then come back to these questions. I feel like if I do that, I'll have a much easier time. These are kind of hard to come up with solutions on the spot. I want to say, see here are a couple problems. Like even building this graph in the first place, I think is going to be too expensive. That's like the first thing. But even if you had the graph, I think processing it would also be kind of expensive to perform that algorithm. I don't think it's good. I don't think it's good. what I was thinking about doing was going the other direction. Instead of trying to find the nodes with the most number of connections, of edges, to actually go for the nodes with the least number. There's basically guaranteed to be a minimum, right? There's guaranteed to be a minimum node, and if you delete all of the edges all of the nodes that are incident on it, um, which has to be done, I think, at some point, um, then, or I guess you start with one of the nodes that's incident. Since this was the least, once you've deleted a node that's incident, it has one less node incident on it, so it's still the least. Yeah, one node that's connected to it. So every node that's connected to it, you want to delete. It'll still be the least. The reason why you want to do this is that no, well, yeah, yes, because suppose you have a node that has one edge connected to it, right? So two nodes are connected. Either you have two options. Either the other node is not connected to anything else, so either node can be deleted, or the other node is connected to other things, and you'd want to delete that node instead of and you know that you would want to delete that node, right? Because that's always true. It's always going to be connected to more things. So yeah, I was thinking that maybe there is actually a way to go the other direction, starting from the smaller nodes and deleting the ones that are incident on it, and that would actually reduce the total number of edges in the graph in a more, I guess, quote unquote, controlled way. Like, you don't actually need to move all of the edges all over the place to update them. So what you would do is, and I think you can, not only can you do
Hello, hello, hello. Oh no. How long has the microphone been off? Uh-oh. No. Oh man. All right, let me give a brief description of the problem. I really gotta go. I gotta use the bathroom. Just quickly, all of the overlapping. So what we're gonna do is create a hash map, unordered map. Hash map. We're gonna hash map all of the intervals, all of the x. We'll call it the x and the y. It's gonna be the x will be the left side of the interval and the right side of the interval. Also, I realize for you guys, this is the right side. This is the left side. That's confusing. But yeah, we'll say the right side of the interval and the left side of the interval. Call that x and y. Right is x, y is left. Right is y, left is y, left is x, left side is x, and right side is y. All of the x values, any duplicate, we're going to use that as the key, and we're going to take the minimum y of all the y's that are mapped to the same x key. And anytime we see a value that's less than or equal to the y value that's already been stored for a particular x value, we're going to increment the count and take the smaller value, or the value that's less than or equal to. And then those pairs basically will have eliminated all of the encompassing and duplicate intervals that start at that have the same x coordinate. Then we're going to dump all those pairs into a vector and sort the vector on the x coordinate. And then we're going to process with an algorithm left to right, sort of a pointer A and a pointer B, call it index A, index B into the vector. And the algorithm is going to go, you have a few different cases. You have A and B don't overlap, which you can check directly. If they don't overlap, you're going to shift A to where B was and shift B one index forward. If they do overlap, then you have two possibilities. Either A stretches further to the right, A stretches further has a larger y coordinate, or B has a larger y coordinate. If A has a larger y coordinate, then we're going to increment the count. We're always going to increment the count when they overlap, but we're going to move A to where B was and B over 1, effectively skipping A or removing A. If it's the other case, then we're not going to push A to where B was. We're just going to shift B over 1. And that's going to be the routine through that sorted list, and that should be it. That'll give us the count as the whole algorithm. It should take 10 to 15 minutes, I think, to program it. I think once we get there. So I'm going to do that shortly. But yeah, again, thanks for watching. I'll be back soon. I'm going to make this a part 1. Rename this as a part 1 and then make it part 2 where I actually program the solution. We'll see how we do. Hopefully it's correct. All right. Thank you for watching. Bye. Thank you for watching. Bye.